fraction we were doing earlier. So something has happened. When we added the E and M, we changed from diffraction, but we didn't totally lose track of the diffraction. It's laying there in the physics somewhere. Can we dig it out? All right, well, yeah, power laws, exclamation mark. So let's try to add a little more electromagnetism, and this is an important part. We're not going to let it be weakly refractive anymore. This is a full-blown droplet of water or a glass sphere or who knows what, titanium dioxide perhaps. Now, when an optical beam comes in, it scatters off of one of the low volume elements, and perhaps it scatters to another one. You've got internal coupling. That's what happens when the index refraction gets big. These guys talk to each other. There's whole kinds of talking to each other inside the particle. And then we need what we call the internal coupling parameter. It will again be related to this Lorentz term, size, and so on. And what we find is that rho prime is less than 1. It's simply diffraction. That would be when the index refraction is fairly small, or when the particle is small, or when the combination of particle size and refractivity is large to make rho prime bigger than 1, then we have to do the full electromagnetism. Now, this is complex, so let me lead you through it. This is the forward scattering, only the forward scattering. At zero angle, remember there was a region of forward scattering lobe. And what we've done here is we've divided it by how much a particle of the same size would scatter if we assumed it was a Rayleigh particle. In other words, no internal coupling. It's another way to say it. So here's rho prime down here. Here's the region, and here's this dashed line here is the dividing line between less than and greater than 1 for rho prime. Down here, notice the scattering in the forward direction is normalized to 1. So that's Rayleigh scattering in the forward direction. That's simply diffraction. That's simply wave. On the other hand, if we go out bigger than 1 on rho prime, we get this fall off. The doggone particle is scattering less than it would have had it been a Rayleigh particle. In some way or another, that internal coupling darkens the interior. It's not as bright as Furthermore, look, I got all kinds of indices of refractions. I got 101 right up to an index refraction of 2. And so I've got all kinds of sizes, all kinds of indices of refraction, and the curve is universal with rho prime. Here's another graph showing this universality. Now this is the full-blown thing. Again, we're Rayleigh normalizing on the intensity on the vertical axis. The horizontal axis is Q times R. So this is a phase function. You make note about it. This would be changing the scattering angle, okay? Change the scattering angle, you change Q. And you can see two plots for 100 and for 1000 for rho prime, but we've got within that 100 a bunch of different sizes and a bunch of different refractive indices. And yet they all lie together because they have the same rho prime. Same thing for 1000. So there's this universality on rho prime. Furthermore, there's diffraction limits here. See this 9 QR to the minus 4? That's the original Fourier transform of a sphere. It's fallen off of that, and where is it going? This is the Fourier transform of a circular aperture. What do you get when you get a really big refractive particle? Well, you can catch them in center field. They're called baseballs. All right? A baseball. A baseball acts like a circular aperture when a light wave hits it because it projects a circular cross-section. And the simple diffraction from a circular cross-section is that -3 power law that I tried to show a little bit ago. Let's see what happens next. Okay, maybe it's my fault. Well, I got Rajan out of here at least. So. It's working.
Maybe I was the problem.
I hope this is my next slide. I'm going to back up. Yeah, that's my next slide. Okay. So what do we need to do? We call this Q space analysis. Obviously, we're working in reciprocal space. right? The Fourier transform space. So we ought to apply this to all types of scattering and also use it as a foundation of our understanding. So what's in front of us? Well, we understand spheres. We can solve the equations for spheres, but what can we do with other shapes? Here are some examples. And here's what's been done in the past with other shapes. So there's this great data set from the Amsterdam group, all kinds of desert sands and volcanic ashes and stuff that flies in the atmosphere, having non-regular shapes. And what do people do? They plot the scattered intensity versus angle, like people have done for time immemorial. Okay? I'm going to take these same data and replot them. There they are. I plot them in Q space, and I got a line. It's a log-log plot, so it's a power law. I've got a power law. Son of a gun. One other thing. The power law is obvious, but notice it's still going up. These people didn't get to small enough angles to see it round over into that flat regime. They missed an opportunity. So there's really two lessons here. Plot it versus Q, you discover power law. Plot it versus Q, and you might find out you didn't get to small enough angles to determine sizes and that forward scattering level. So here's some examples of theory out of our group. These are Gaussian random spheres, a well-known simulation of sand grains, et cetera, et cetera. And you can see as the refractive index increases, there are power laws. The slopes are decreasing with increasing refractive indices. There are also Gounier regimes and forward scattering regimes. We've compiled a whole bunch of different data on non-regular particles, and we plotted, you know, what? How many points are there? 50 points. We plotted 50 graphs. They're all linear when you plot them versus Q space. And this is a trend of what the exponent is doing as that phase shift parameter, that rho parameter, keeps increasing. Small rho, there's the diffraction limit of -4, and then it rounds off like this. We do not know why. Right? This is an empirical result. It's not published yet. We don't know why. Let me remind you, I've spent 3 decades of my life studying fractal aggregates. And also, as Amit showed earlier, it works for both 1.8 fractal aggregates and super aggregates. And if you don't like my theory, you can use this theory, okay? So, but you better have studied Jackson's electrodynamics recently to understand it. And if you don't like that, you can do this, okay? Who wants to do this for your comprehensive exams for your PhD? I didn't think you did. No, neither do I. So, all right. So finally, I'm going to finish up here pretty soon. One thing that we certainly learned is small angles are important. So we built this device where we've got multi-channel arrays here, and we can detect down to 0.3 of a degree. Simply said, it's diffraction. Simply said, it's lambda over d. If you got a 10-micron particle, and if you got a 0.5 micron green wavelength, you got a 20th of a radian. 20th of a radian is 3 degrees. So if you want to see a 10-micron particle, you better scatter it 3 degrees or less if you want to measure the size. It's just sophomore physics. So we built that thing, and what we need to do, well, I guess there's a bunch of things to do. Polarization's involved too. We can't forget that. But in order to understand, I believe, scattering from any morphology, we're going to have to use this Q-space analysis. And we're going to have to go to small angles. And the other thing that comes up, is we talk about scattering from irregular shaped particles, and then we have to stop and pause and think, what the heck do we mean by irregular shape? We got lucky with fractals about 30 years ago. Aggregates, for a while, people called them various weird names. Random aggregates. It was only until Mandelbrot and Forrest and Whitman and so on managed to show that they had scale invariance, managed to quantify it with the fractal dimension. Now we can describe and quantify, and we can say with that morphology. What's the morphology of a sand grain? What's the morphology of collapsed soot that's been hydrated in the atmosphere and so on? So I think concomitant with this is the real space description as well as the Q space description that we have to convey. And I think that's it. Power laws everywhere.
Thank you. Thank you. Our next speaker is Kirk Noblespeech, scientist in NASA Ames Research Center, and he's going to give a perspective of